Now let's consider beam deflection. Why would we be interested in beam deflection, and what is it? Well, beam deflection is just a vertical change in position of the neutral axis of the beam. So if we apply loads to a beam, you can imagine that that beam is going to deflect in order to carry the load, and in the process develop stress within the beam and so forth. Why would we bother calculating this? Well, there are actually many reasons. For one thing, we don't want the beam to fail, and failure doesn't necessarily just mean fracture. It could be that the beam is out of position where it can no longer do what it's supposed to do, or whatever its intended function may be. Sometimes we don't want to see sag in long spans. There can be problems. I just put a beam in my garage. Well, I guess I didn't just do it. It's been probably 10 years. Time seems to fly. But I put a beam in my garage because when I bought my house, the owners before me had changed the garage into living area, but it wasn't all that good. There was some mold in it and things that I needed to clean out, and I did. But I thought, I would rather have this space as a garage again. So I enclosed it and turned it back into a garage. I ended up putting my garage door on the back side because I hate the way that houses look when the garage door is out front and center. It just looks strange to me. So I put my door in the back. There's windows in the front, so it just looks like there's more of the house, and then I can enter the garage door from the back. Well, I wanted it to be nice. If I'm going to build this myself, I'm going to build it a two-car garage, and so that's what I did. But I didn't really want to have two separate doors, so I got one 16-foot door and I installed it. Of course, in the process of framing it, I needed a beam that would run over 16 feet, right? About 16, 17 feet, something like that, maybe a little less, but so that I could support the ends of it. But if I had built this out of a beam that wasn't very stiff, then that beam would sag and it would look awful. Even about an 1/8 inch of deflection or so, your eye can pick that up and see it. So I think I calculated the required beam geometry based on a maximum of 1/16 inch deflection in the center, given the roof load that was going to, the beam had to carry and so forth. And that way it looked okay. It didn't look like it was weak or something. Of course, if a brittle material is attached to a beam and the beam sags too much and can't support it, then that brittle material fails. Things like plaster or concrete can crack very easily if the beam is supposed to support it and sags excessively. So when we think about beam deflection, a lot of times your intuition can help you understand what's going on. Figure A shows two different weights or two different external loads applied to a beam that is simply supported at either end. Now if we apply these loads, you can imagine the beam is going to simply deflect downward. One thing that your intuition may not tell you, if you just have one of those loads, the maximum deflection will not necessarily occur directly under the load. As a matter of fact, that's what we already saw in A, right? Sometimes the maximum deflection is under the location of the point load, sometimes it's not. So it's a combination between the externally applied loads and the reaction at the supports that bends the beam. If you think about a diving board, for example, that's as in figure C, where there's a point at the back that prevents the rear of the diving board from moving up or down, and then a pivot on the front that only supports the diving board upward. A lot of times it's actually connected where it could provide downward force, but if your weight is out on the end of it, you're bouncing out there getting ready to jump into the pool, well then the deflection where you're at is going to be downward. It most likely would be well, in fact, it depends on the geometry of the beam. I was going to say it would be the maximum deflection, but that's not necessarily the case. Anyway, there would be obviously deflection directly under where you are, but there would also be deflection of the board between the supports. Now, if someone's standing behind you, waiting for you to jump off the end, well, then you can see the deflected shape that could occur in D. Now, of course, the magnitude of weight 1 and weight 2 are going to affect the exact amount of deflection. But understanding this and thinking about it is really important. For example, let's say that I'm waiting for my daughter to jump off. She's a lot lighter than I am, so I'm weight 1 as in figure E. She's weight 2 as in figure E again, and so she might actually be higher, right, deflected upward because my weight is so much larger than hers. It's possible then if we switch positions and she's waiting behind me, say she's jumped in and come back around and getting ready to jump in, but I'm taking my time out on the end, well then it's possible again that because my weight is so much larger that she might be deflected upwards, whereas I'm deflected downwards. And of course we're just talking about standing there statically. If you have a cantilevered beam, well then, obviously the cantilevered beam is going to deflect downward as weight is applied to it. because the fixed end can't rotate. So it's important to notice in these figures that so far we've been dealing with point supports or simple supports where the beam is allowed to rotate about that point. Think of a pivot point there. But if you have a fixed end or somewhere the beam is fixed, then there's no rotation allowed there as well as no translation. So you can support a moment and forces with a fixed support. Obviously, if a beam is fixed in the center, we can consider it as two separate beams. It's not going to deflect or rotate in the center, so they're independent from one another. In the last case, case H, there is not only a fixed support, but there's also a large load sort of in the middle going upward and a large load at the end going downward. Now, there's a key difference between an applied load and a reaction load. Notice that an applied load, there can be deflection wherever there are applied loads, but wherever there is a support, whether it's a simple support or a fixed support, there can be no deflection. And there's a fundamental difference between those two. Because as we consider beam deflection, one of the things we're going to get into are indeterminate beams. That'll come a little bit later. But in indeterminate beams, these are statically indeterminate. You can't calculate the loads and the stresses and so forth within the beam without considering the deflection of the beam and calculating the deflection of the beam and realizing at what points the beam will not deflect because it's not allowed to, because those points are fixed. This is very important in order to solve these types of beams. How much should we allow a beam to deflect? Well, a lot of times it's determined by aesthetics, like my garage door that I mentioned. I don't want it to look bad, I want it to look strong. Of course it has to support the weight of the roof, but the beam could actually deflect quite a bit and still safely support the weight of the roof, even with a snow load. But usually you don't want them to look bad, or maybe there's an application where the beam, as I said before, would not function properly if it deflects too much. And so a lot of times deflection limits are determined just by knowledge of typical applications, same but different types of machines, for example. There are some generic rules, but I'll refer you to page 459 to look at those. Now, when we make a beam diagram, we need to very clearly indicate what the loaded beam looks like, the shear diagram, the bending moment, and then what we'd really like to do is also draw the slope and the deflection. Now, the slope and deflection, I'm not going to require that you draw these and make them extremely accurate, but you do need to have some understanding of what's going on. So let's take this simple beam, which is simply supported at either end, and there's a load P that is not in the center. It's offset just a little bit. Now, if we consider this, notice that load P is just a straight arrow, right? But notice the reactions at A and B have horizontal lines through them. Those horizontal lines are really important because what they tell you is that point A and point C, is not allowed to deflect at all. So if you go all the way down to the deflection diagram at the very bottom here, you notice that point A and C at either end are just on the original beam line, the neutral axis line. So they haven't moved at all because the reactions at that point, at those points, point A and C, are such they do not allow any deflection. Of course, at point B, where the load is applied, there is significant deflection, but not necessarily the maximum deflection under that point. Now, how would you find where the maximum deflection is? Well, I'll show you all that a little bit later. But remember, we still have to be able to draw shear diagrams, so our shearing force diagram you can see, and bending moment diagrams. We haven't gotten out of that. But it's also helpful to be able to at least intuitively understand the angular rotation of the beam. So if we start on the left-hand side, it makes sense it's going to angle down, right? So if it angles down, well, what that means is that there's been a deflection, an angular deflection, and at the other end, at C, it angles the other way, right? And so you can see that at A, all the way on the left, there's a negative angle, and all the way on the right at C, there's a positive angle. Now, there are some other points defined in between. There's a point D and a point E. Those are important points as well, because we can, they're not necessarily unique and important. They're just points where we're trying to indicate that there are angles at all these different points where we could talk about slopes and deflections of each point. But again, we're not going to bother calculating this much in this course. What we're really interested in is more the intuitive understanding of the angular deflection and the linear deflection, and then of course our ability to calculate moments and forces. Shearing forces will be really important so that we can calculate deflection. So we will calculate deflection, but most of the time we're mainly interested in linear maximum deflection. Not always, but usually. So what determines a beam stiffness? I mean, the stiffer the beam, obviously, the less it deflects. What sort of variables do we have control over? Well, we get to select the material that the beam is made from. In my garage, for example, I had plenty of pieces of wood. I think I ended up using 2x12s or 2x10s, I don't remember now. And I just sandwiched them together because it was a 2x6 wall, so I had plenty of space to add plenty of support, and it's worked fine. But if I could not have made a beam that would carry the load without excessive deflection, I may have had to change the material. As a matter of fact, I could have used steel. Now, steel's more important. I already had the wood, so I used it. But I did I performed the calculations first in order to ensure that the wood would not deflect excessively, and of course that it could carry the load. But I could have changed material. I could have bought an I-beam or something. Maybe an engineered beam would have been more stiff. The other thing we have control over is the shape. So basically, the second moment of area, the moment of inertia I, is sort of a shape stiffness. The farther you can get area away from the center line of the beam or the neutral axis of the beam, the stiffer it's going to be. So beam stiffness is really the product of these two. It's the material stiffness, E, the elastic modulus, multiplied by I, the second moment of area or the moment of inertia. And so if that's the stiffness, then the deflection is going to be less if the stiffness is higher, right? So it's an inverse relationship. So the bigger we make EI, that product, the less deflection there's going to be. So it's really important to see this because in all of the beam equations we end up writing, you're going to see 1 over EI in all of them. That's a very common multiplier, and it's because it's representing the geometric stiffness and the material stiffness together. So how on earth are we going to calculate deflections? Well, there are actually several methods, a couple of which we'll focus on and a couple of which you'll be glad to know we will not use. There's the formula method, I'll show you that in a moment, and there's also superposition. There's successive integration. Don't panic, we're not going to do that. I know most of you guys probably don't like integration very much, so we're not going to do that. It's a powerful method, it's useful. You got to pick and choose in a class like this, and so that's one of the things that gets sacrificed because we do so many, or we perform so many lab experiments and projects and things trying to help you really understand stress and what it is. And so the successive integration is nice, but it's really not necessary. Most of the time you can get the same results using formula, and it's a little easier anyway, at least conceptually, I think. And then there's also a moment area method. We're not going to use that either. It has to do with the deflection diagram, so we won't do that. We'll use the formula method and superposition. For the formula method, all you really need to do is go to the back of the book, to the appendices, and find an example model that matches the loads and supports that you have. Now, to use these equations and these formulas, the beam cross-section has to be uniform for the whole length. So you have to have a beam that is the same and does not vary. Its cross-section can't vary along the entire length. But that's very common for beams, so it's not really much of a restriction. I mean, I guess it is if you have a beam that's not uniform, but most beams are uniform, so it doesn't matter most of the time. So you just, depending on what kind of beam you got, whether it's a distributed load or point loads and supports and things, you just find one that matches. And it's all parameterized. Instead of being actual numbers like I've shown here, it would have, length L and distance to the load, A, for example, and then B is the remainder of the length. And you just plug in the numbers you have in your problem and you solve it. It's pretty easy to use. But what if you have a beam that's a little more complicated than the models that are available in the back? Look at the beam on the right, for example. There's not only a distributed load, there's also a point load in the center. So we've got this 800 pound per foot distributed roof load, and then a 2,500 point load in the center. There are reactions out at the end. Notice that I know that the outer two are reactions because there's horizontal lines through them. Okay, how on earth would we calculate this? What would we do? Well, we would take two different models and simply add them together. That's what superposition means. It means that we can simply add the results from two models. So we'd take the model that you see at the top with the point load to model that 2,500 pound load. We'd calculate how much Y1 is, how much the deflection is. Okay. And we would add to that the deflection from the 800 pound per foot load Y2. Add them together and there's your total deflection YT in the combined beam. Now, if the distributed load was acting upward, then we'd subtract Y2, right? Because the distributed load would be pulling up on the beam, whereas the 2,500 pound load is pulling down. And it's not exactly clear which way this is, but since it's a roof load, it's probably intended to point downward. But it would work just as well if this was a distributed load pulling up. Maybe there's wind blowing across and a low pressure, and so there's a distributed load pulling up on this beam. In that case, Y2 would be upward, and we would simply take the difference between Y1 and Y2. And by the way, this works at any point along the length of the beam. So if you want the deflection, say, a quarter of the length down the beam at about 4 foot from the end, we'll just calculate the deflection from the two loads, the 2,500 pound load and the 800 pound per foot load, at 4 feet from the end, which is a quarter of the length of the beam. Add them together, and you've got your deflection of the total deflection at that point from the two loads. So this is pretty easy to use. It's not all that difficult, and really the superposition method is just extending the formulas and realizing we can add the deflections together from the formula.